This tutorial is a combination. There's a little bit of lecture here, but clarifying about what the two-body problem is, excuse me, and Newton's third law. And we'll apply this twice. So what we mean by the two-body problem is that we have two objects that are getting accelerated. And let me draw it like this. So we have a big mass here, and let's call this 30 kilograms, and then a smaller mass here that comes in at 20 kilograms. And we apply force to move it. And we're going to apply a force of, let's cute, nice round numbers. So let's apply a force of 100 newtons. And the prompt is find the acceleration and the force between the two. Okay. And of course, these are resting on a surface, which will enable us to put a spin on it and turn on friction as well. So I'm going to share my screen, and we're going to go out and take a look at some files that are loaded up on Canvas. And I just call them the donkey and the cart. So one of the things that we know about Newton's third law is that it's sort of the colloquial way of expressing it is for every action there's a reaction, but that's often misconstrued and into more of a cause and effect situation. And I'll give you an example of that. So I'm going to share my screen, and we're going to go out to a document that is on Canvas. It's called the cart and donkey problem. So here is this this donkey who's not really happy about being tied up to a cart, and the donkey argues that as soon as he starts pulling the cart's going to pull back on him with the same force, right? So for every force, there's an equal and opposite force, and the two forces are going to cancel. So very nihilistic donkey, what's the point in life? Very existential. So what we can do is we can break up and start talking about action and reaction pairs. Forces don't really come in pairs. It just depends on your point of view. It's all relative, right? So if there's a force between the donkey and the cart, they're both going to feel the same force, but they'll feel in opposite directions. So we can list all the action and reaction pairs, but then reorganize them into what are forces on the donkey and what are forces on the cart. And that's already done in this problem. So you can see that we have a bunch of action reaction pairs, and they are color coded. So here's one. Donkey pulls cart left, and that's a force to the left, and it's in red. And then over here, cart pulls donkey right, and that's a force to the right. And it's labeled in blue. So both of these are sort of right here. And that's called an action reaction pair. And we can keep on going because the other players involved are friction with the ground. The donkey's pushing on the ground's pushing the donkey, and the cart too is having friction with the ground. But if you take a look at how they're color coded, the red forces are forces on the cart, and the green forces are forces on the ground, and the blue forces are forces on the donkey. So when we rearrange them, it turns out that if we're trying to figure out whether this is going to move or not, we really have to compare apples to apples and oranges to oranges. We have to compare forces on the donkey to other forces on the donkey, but not mix them. And that's where the action-reaction pair got mixed. Cart pulls donkey right, and donkey pulls cart left. But these two forces, even though they're equal and opposite, they don't cancel because they act on different things. That's a really big idea. Action-reaction forces don't cancel, These two don't cancel because they act on different masses. And then that's the bottom line. So all that has to happen is the donkey has to pull harder on the cart than friction, which is, what our common sense would say anyway. So then if we take a look at this situation, and this is out of the slide deck, that we have two masses here and they're being pulled by 40 newtons worth of force. So here's free body diagrams labeling everything. But there's tension in this cord that connects the two boxes. And at what point do we care about that tension? So with the two-body problem, what we do is first we solve the overall system to find the acceleration. And you can see that the tension is an internal force. And that's why we talked about it. Newton's third law, action-reaction. Here's our action-reaction pair happening right here. But for starters, the 40 newtons is trying to accelerate both boxes. So we add the masses together, that's our system, and then divide through and find out the acceleration. Now we can look at the tension in between the two because the tension is what's responsible for accelerating this box at 1.8 meters per second squared. So let's just look at the 12 kilogram mass, and the only force acting on it is the tension. And it's making this 12 kilogram box move at 1.8, so we get 22. Or we could look at the 10 kilogram box, if that equals MA, where the tension is pulling back on it. So 40 minus the tension causes 10 kilograms to accelerate 1.8. Notice we've broken the system up. We're treating the 12 and the 10 separately at this point. And of course, we get the same result. So let's go back and take a look at the problem that we started off with. The force between is an internal force because the 30 pushes on the 20 and the 20 pushes on the 30. But the best way to do this is to start off and solve the system. And that means we have F net equals MA. There's only one force acting on it, and that's 100 newtons, acting on the sum of those two masses, which is 50 kilograms, and an acceleration. And so my acceleration is equal to 2 meters per second squared. And then now we can isolate. So the force in between was not a player when we did the whole system because it's an internal force. But if we isolate the 20 kilograms, then you can see that we've got, there are 20 kilograms. Oh, I did need that, sorry. And that's being accelerated by this internal force, but we actually know that the acceleration is equal to 2 meters per second squared, which is, we did know that at the start. Now, Newton's second laws can become much easier. So F net equals MA. And the only force that's acting on it is this mystery force. So F, and it causes our 20 kilogram mass to accelerate at 2 meters per second squared. And so that's 40 newtons. Now, a lot of people would say, shouldn't I be able to do this with ratios or something like that? Yeah. So the total mass is 50, and 20 kilograms is 40% of the total mass. And so it gets 40% of the force. Right. Okay. Now let's turn on friction. So let's repeat. And coefficient of kinetic friction, have to be careful of this. So 50 times that's going to be, I want to make sure it moves. So we'll make it pretty slippery. So 0.10. Great. Okay, so now when we reconsider what is going to happen, so I'm going to just repeat this diagram really quick. And we are applying a force of 100. But now we're going to have friction as another force. And we still have this internal force happening. But now we also have a force of friction that is in opposition. So what are we going to do with that? Let's just pause for a second and then calculate the friction that's going to be working on each one of them. Right, so for the 30 kilogram mass, then force of friction is the coefficient of friction times the normal force, and the normal force is just equal to mg since we're on a level surface. And so I'll type in the numbers for that. And 0.1 makes the math easy. So 0.1 times 30 times 9.8. Yeah, so that's going to be a force of friction of 2.94 newtons and the 20 kilogram coefficient of friction, mass, and gravity. And so I'll just repeat this calculation and do it for 20. That's 19.6. And then total, of course, it happens when I add these two together. So that's looking like a nice round number, right? So I think that's going to be 49. Okay. All right, so we're taking care of the friction part. So F net equals MA. And we're doing our system, which is both masses. So I'm going to have 100 newtons being opposed by friction. And I'll add these two together. And what friction should I use? Boom or boom or boom? Should I use this and then also subtract that? But then why not just do the total? Okay, so we'll bring our calculator in again. And so 100 minus this, whoops, minus negative, and see what that goes. And then we'll divide that by 50. Okay, now the acceleration is equal to 1.02 meters per second squared, which makes sense because we had 2 before, so it should be less. Same applied force, but now there's friction. So that makes sense. And now isolate. The 20 kilograms, and we could isolate the 30, but it's, you can see from our diagram, it's just going to be more forces, right? And so we have our 20 kilogram, and it's experiencing some forces. So there's mystery force here. And then we've already calculated friction, so that was pretty smart. So we have, and that's the friction on the little one, so that's 19.6. And we want to find it, what the force is in between the two. So F net equals MA. And this is just a reminder, we're going to put the cause of the motion on the left side and what the motion's doing on the right. And so that's equal to 20 times, and what it's doing is it's accelerating at 1.02 meters per second squared. And then I have mystery force, that's what I'm looking for, minus friction, which we already calculated, it's 19.6. So we'll multiply this out at 20.4. And then when we add these together, the force divides itself up proportionally again. 40% of the mass gets 40% of the force. And why is that? The reason for that is that friction actually depends on gravity and depends on the mass. So we wouldn't really expect anything different. So this was a longer tutorial, but I think you'll find it really helpful. We're going to take a look at two-body problems that are vertical next.